Good morning everyone, I'm Francesca Donnaloja and today I show you in silico results about lamina mechanical characterization. Lamina is the nuclear cytoskeleton and it consists of a mesh composed by tetramers of lamin proteins arranged to form a structure which provides mechanical support to the nucleus. Lamin monomer has a highly repetitive structure that mainly consists of a head, 4 coiled domains, and each fold domain. It is known that lamins rearrange according to external stimuli to make the lamina mesh suitable to absorb the stimuli from extracellular matrix. In this context, to better understand the lamina behavior and its effect of rearrangement, several studies tried to characterize lamina from a mechanical point of view. Both computational and experimental techniques were implemented, but both protocols highlighted several drawbacks. Indeed, experimental techniques such as micropipette, AFM, and compression analysis estimated the wall lamina mesh features approximating the lamina properties to those of the wall nucleus. Instead, to comprehend the stiffness at molecular level, molecular dynamic simulations were used. Anyway, these studies focus only on the dimer configuration and did not estimate the viscosity term. In this context, we designed a computational protocol in order to estimate both the stiffness and the viscosity term of the lamins. And in particular, we investigated the mechanical characteristics of CC1b domain, the most studied domain of lamin monomer, via in silico crypt test, comparing the different contribution of the monomer, the dimer, and the tetramer configuration in relation to the H-bonds occurrence. First of all, I extracted the CC1b domain from the longer array X solved domain available in Protein Databank database, and I solvated it in a water box. I equilibrated the protein for 600 nanoseconds, and I extracted 3 protein models to verify the reliability of the results. For each model, I extracted the monomer, the dimer, and the tetramer configuration. I applied step force to each chain of each configuration to simulate a crypt test condition. 3 different force values were tested, and to simulate a tensile deformation, I fixed the N-terminal atoms out of each chain, and I applied an instantaneous step force to the C-terminal residue. To make the monomer, the dimer, and the tetramer configuration all comparable to each other, during the elaboration phase, I reduced all the configurations to an equivalent single chain. In particular, first of all, I extracted the average coordinate of the fixed atom and the average coordinates of the stirred atoms here reported in green. Then, the equivalent chain was extracted to connect in the green points. For each configuration, I calculated the equivalent chain elongation over the simulating time. Then, fitting the data with Kelvin-Voigt equation, I extracted the Young's modulus and the viscosity coefficient for each condition. On the left, the Young modulus, and on the right, the viscosity parameter for all the analyzed configuration and for all the 3 applied force values. In general, it was possible to observe that the Young modulus is about 0.4 gigapascal and that this result is almost consistent with all the data from the literature obtained via both experimental and computational methods. And this aspect supports the reliability of all the estimated parameters, even though no data are yet available in literature for the viscosity term. Analyzing in details the collected data at the same force value, the Young's modulus doesn't change from monomer to tetramer configuration, suggesting that it is mainly influenced by interchain bonds, which are almost constant among all the configurations. Instead, considering the same configuration but different force values, the elastic component increases, indicating lamina stiffening proportional to external load. The intrachain bonds are therefore able to resist to high force intensity induced by internal rearrangement of residues. Instead, the viscosity parameter increases with the configuration complexity, suggesting the interchain bonds influence, And considering the same configuration, the viscosity parameter decreases with the force increment, suggesting that the interchain bonds are not able to dampen when the force increases. In conclusion, considering the highly repetitive structure of the lamina that is mostly characterized by a coded domain, I propose that the mechanical parameters here estimated are representative of the whole lamina filament's behavior, at least from qualitative point of view. In light of that, we can conclude that first, lamins behave as viscoelastic material, and then that lamins are able to modify their stiffness to protect the nucleus from external stimuli, thanks to both intrachain and interchain H-bonds contribution. These results may be correlated to several pathologies called laminopathies. Indeed, mutation in lamins cause several heritable diseases called laminopathies, such as dystrophy, progeria, and age-related disease. Even if their pathological mechanism remains so far elusive, mechanical defects in nuclear structure is one of the most plausible hypotheses. Indeed, as showed by AFM test, it is worth noting that several single-point mutations causing progeria affect the laminar stiffness. And in line with this, we propose that the mutation could alter the H-bonds at molecular tetramer level, affecting the laminar capability to support external stimuli. Further investigations are therefore required to verify this hypothesis. In line with this, as future perspectives, I would like to characterize the different laminar regions to confirm its viscoelastic behavior. Then I will repeat the same protocol here developed to investigate the single-point mutation effect on mechanical parameters. And lastly, I would like to validate the here obtained computational findings by AFM experimental technique. So thank you for your attention.